this presentation, I am going to discuss noise reduction for task-based functional MRI using NORDIC and KWIA. Functional MRI has found great potential for a wide range of neuroscientific and clinical applications. However, high-resolution fMRI, which delineates finer brain structures and connectomics, has been obstructed by its low signal-to-noise ratio. Recently, NORDIC denoising method was proposed to suppress the noise components of image series that cannot be distinguished from thermal noise. Our group also developed a denoising method, namely KWIA. KWIA performs spatial temporal filtering of image time series by taking advantage of the characteristics of k-space data. In this work, we quantitatively evaluated the performance of NORDIC and KWIA methods in denoising by comparing them to the standard manufacturer reconstruction using task-based high-resolution fMRI datasets. We used the 7 Tesla magnetom Terra with 32-channel Nova head coil to collect data. We recruited 2 subjects. Each completed 1 T1W image and 4 runs of fMRI visual task. During the task, the subject passively viewed a blinking checkerboard for 20 seconds, followed by 20 seconds white fixation in the middle of the screen, and etc. Subject 1 had 1 mm isotropic resolution during the functional scan, and subject 2 had 0.8 mm isotropic resolution. For each functional MRI run for each subject, the data was reconstructed using 3 methods: standard, KWIA, and NORDIC. Each reconstructed fMRI time series was realigned to correct motion and high-pass filters, then co-registered to the anatomic image. No spatial smoothing was performed. Each pre-processed fMRI data was then analyzed using a general linear model with predictor for visual stimulation and nuisance regressors for motion parameters, and t-tests were conducted for the contrast of visual stimuli versus fixation. Based on the t-statistic map from the standard reconstruction, 2 regions of interest for left and right visual cortex were generated. Average fMRI time series data from these regions of interest were extracted for each run and reconstruction method to compute the respective temporal SNR. A one-way ANOVA was conducted to evaluate TSNR differences for the 3 reconstruction methods. NORDIC outperformed KWIA and the standard method as reflected by more consistent and larger extent of visual cortex activation in T-maps for each fMRI run and across the 4 fMRI runs. This is a t-test result for subject 1 with 1 mm isotropic resolution. This is the t-test result for subject 2 with 0.8 mm isotropic resolution. The ANOVA for TSNR revealed significant effects of reconstruction method in both hemispheres. In the V1 region, the post-hoc analysis with Tukey correction indicated for subject 1 NORDIC had significantly higher TSNR than standard in both hemispheres. KWIA had a marginally higher TSNR than standard on the right side. For subject 2, NORDIC had significantly higher TSNR than standard, and KWIA in both hemispheres. In conclusion, we compared two different noise reduction reconstruction techniques against the manufacturer standard reconstruction. We found that both techniques improved single-run statistics and consistency across runs. Analysis of TSNR confirmed improved data quality in the time domain that facilitates time series analysis for task fMRI. While NORDIC provided excellent performance and is a parameter-free approach, it is computationally demanding and requires phase and magnitude data for denoising. Our KWIA approach also improved noise characteristics as compared to the standard reconstruction. KWIA might be an easy to implement and computationally fast and straightforward alternative to NORDIC for high-resolution fMRI data.